Hello, I'm John Elder, and I am doing a series on the deadly dozen data science mistakes. And today we're looking at number 3. It's a mistake to rely on just one technique. Lots of people have their favorite techniques, and it's great to master something. But if you stick with one technique, you can leave a lot of performance on the table. It's great instead to be very good at several. And I suggest a simple toolkit of at least 5 techniques. Obviously, classic linear regression, very powerful, always worth trying, at least as a baseline method at the very least. Decision trees are also quick to run and give you a lot of insight. Neural networks can be very powerful, and I recommend nearest neighbors, pretty much an underutilized technique, but very different in concept from the others, and sometimes it can save the day if you select variables correctly. That's the thing, is each of these techniques have strengths and weaknesses that are different from each other, and you can learn from each one. Lastly, I recommend an ensemble method of some sort, and the best, easiest one out of the box is one called random forest, which uses trees that have different training data based on resampling and also emphasizes variety in the features that it uses. It sort of penalizes, or it encourages a wider variety of features than a single decision tree would ever use, and that can be useful. So this is a great toolkit for trying multiple techniques. Now, it's a lot more effort than working with a single technique, so I want to justify and encourage the use of multiple techniques by showing how valuable they can be. First of all, if you try multiple different techniques, you'll get a distribution of results. You'll get like a baseline from a normal method, and that'll help you know how much the fancier method is adding to it. And this distribution also can tell you if everything finds it hard, that's a bad sign. It might be very difficult to get good enough performance out of your data if you try multiple techniques and they all have a hard time with it. Likewise, there are some problems where all the techniques actually do pretty well on it, and it can tell you have a pretty easy problem, but you want to be careful it's not too easy. In other words, is there some information in the data that actually isn't viable in the real world? You have a leak from the future or something, and we'll talk more about that in a little bit. So the distribution of results can tell you something all in itself, and the fact that these techniques all use sort of different vocabularies for building their models. Some of those vocabularies can be appropriate for a problem sometime, so you definitely want to try a variety of techniques. But another thing you get out of the multiple models is you might want to use them together in an ensemble. I call it bundling, when you have multiple heterogeneous models and you use the predictions from all of them to get a better prediction. And we'll talk more about that in a later mistake. Each method also teaches you something. It teaches you either about variables or cases. And some of the things you can learn from the methods are things like variable selection, which variables happen to be most useful. Stepwise regression and decision trees both do variable selection. The other techniques don't. And so they can benefit from the wisdom gotten by one. Technically, it's always possible that a variable not liked by one will be really valuable to the other, but more often than not, if a technique has sifted through lots of different variables and found its favorites, that's a great place to start with another technique that can't do variable selection. You can also learn new features. Decision trees, for instance, have interaction effects, if this and that. And if that proves useful for the tree, you could try a feature like that and use regression and neural nets and things like that. And they can suggest, that's the interaction effects, but they can also suggest other kinds of new features, other kinds of nonlinear transforms and things like that would help you. And on cases, you can see if there are clusters of cases. Sometimes a great feature is the distance from one case to a cluster that has a certain importance to it. So if you can do any kind of understanding of clusters of cases that behave similarly, that can offer a lot of insight. Outliers have huge effect, especially on the global models like regression and neural networks, where you have one single equation fitting across the entire space. Therefore, every data point affects the model everywhere else. Unlike with things like decision trees and nearest neighbors, where they have much more local influence. And so the outliers are less dangerous to those methods, and yet identifying them can help you do better on the other methods. Likewise, a leverage point can be thought of as an outlier in the input dimensions. it typically has a huge amount of leverage on the weight of a regression, let's say, and then one single point can outweigh 10,000 other points if it's properly positioned, and that's a danger. You don't want that to happen. So these can be identified with some of these methods. And lastly, what if your model is really having a hard time fitting certain cases? Maybe you're even using an ensemble method like boosting, which uses a sequence of models where it puts more and more emphasis on the cases that you're missing. Well, there's a good chance that case is mislabeled. Anytime human judgment is used in labeling outcomes for training, there's a possibility of a mislabeling, and of course, that will infect your whole modeling process. So again, running multiple techniques, looking at them and understanding what they're telling you can really help you, even if you only settle on a single model form in the end. And let me give two stories to illustrate that. The first is with neural networks. So a bank was trying to build a model to predict future interest rates, since that's so informative about the relative importance of different kinds of assets and so forth. And they hired a very confident fellow with a PhD in computer science who'd edited a few books to build the best model they could. And neural nets were hot at that time. So that was the hot off the presses thing that we're going to use. And the neural net returned 95% accuracy at getting the answer. And the board of the bank realized that was too good to be true. The modeler wouldn't accept that. They thought no one as clever as they had yet attacked the problem. But the board had a third party come in and try to figure out what had gone wrong. They would love for it to be true, but they feared it wasn't. And indeed it wasn't. It took about 3 days, which in retrospect is kind of embarrassing, but it took about 3 days to figure out that the desired output, the future interest rate, was one of the inputs. And so the neural net was only losing 5% of the information as it went through. So obviously that's a leak from the future. This is a major mistake we'll study later in the series. However, if someone had run a regression on this same problem, it would have said y hat equals x5. It would have immediately have identified that the output and the input were identical, and they would have realized it so much more quickly what the problem was. Again, why not just run a regression? It's so easy. You've done all the data preparation for one method. It's not that much effort to do these other methods. In fact, maybe 5 or 10% extra effort to do a really good job on each of these methods. And yet there's a secret here, it looks to your client or your boss like you did 5 times as much work. So it's another good reason to try multiple techniques. The last example I want to give has to do with decision trees. We were trying to predict upselling for AAA. They have a large group of people in their emergency network, and they try to upsell them more profitable insurance when possible. So who's going to upsell? It's not a lot of people buy. It's only about 1% of them buy. And so how can you identify those that you want to spend time with talking to? So a decision tree is a great place to start for lots of different reasons, which I actually explain in the blog. I give like 8 great reasons why, even though decision trees are typically the least accurate method, there's 8 other great reasons to use them. And so we were in initial stages, especially, it's a great technique to try. So we ran a model, and the very first split on a variable, we'll call it X11. And if it had it was a categorical variable. It sometimes had a code in it, E, F, L, P, that sort of thing. If it had any of those, it went to one side, and those people bought insurance. 100% of those people bought insurance. And remember, that's astonishing because only 1% of the original population does. But 20% of all people who bought insurance fell into that node. And the other way was if it was missing. If that code was missing, you had a harder problem that went on and on and on, had many, many splits, but probably none of these leaf nodes, none of these terminal nodes were ever higher than 2%. So this is too good to be true. And the client originally thought, well, no, that's probably really useful. This is great. But they couldn't explain what X11 was, and we eventually found that it was a cancellation code. So it was the code that they recorded when someone canceled the insurance they bought. So obviously that cancellation is occurring after the purchasing of the insurance, not before. So yet another example of a leak from the future. So the leak from the future was only in some of the cases that had this code. And by the way, that points out that they were losing 20% of their, they had an attrition rate of about 20% in a year. So that was a problem to work with too. But anyway, it was only with certain cases. If you had run, let's say, a regression on that problem, you would have had to explode out the categorical variable into several binary variables, E, yes or no, F, yes or no, that sort of thing. And those binary variables would all receive some small positive weight saying they had some predictive ability toward getting the answer toward a 1 for insurance versus a 0 for not buying it. But it would have been very hard to interpret why that was. And the decision tree instead is segregating a bunch of weird cases and letting you focus on that, which is exactly what you needed. So decision trees I think of less as modeling methods and more as methods that identify interesting subsets of the data. So I'll just want to leave with the issue. Don't just stick with your favorite technique. It's got a lot of benefit to trying multiple techniques and being good enough at them to understand what they're trying to tell you.